Sir,
Philip,
let's get started.
This time you may start.
Okay, good morning, good afternoon, everyone. My name is Philip. I'm a general manager at Dryden Aqua. I'm responsible for the markets in America, in Asia, and Australia.
Yeah, good morning, everybody. My name is Dominic. I'm also general manager. We are a huge company. That's why we need two.
Yeah.
No, to be honest, we couldn't agree who is the boss, so we said we have two bosses. I'm responsible for the operation in Africa and in Europe.
Hello, everybody. Here is Jochen. Yes, I'm the division manager for water treatment. Joined our great team here a year ago, and I'm happy to be here and to talk to you.
And we call you Mr. RO.
Oh, yeah. Mr. RO, water treatment. Yes.
Yes. And how does this come? You know, you joined us, and of course we know you. You're really expert in RO, and I heard your father was the inventor, or at least he was really one of the pioneers in RO.
So, he was pioneer. Yeah, he was pioneering the membranes here in Europe, Middle East. So I think he was key in bringing the membranes to the market. Yeah. So I was actually born with the membranes.
With membranes. So instead of mother milk, you got permeate.
I got some permeate. Yes.
Good. That's why you're here, and that's what we want to discuss. And
good.
I think we start with the presentation.
Yes. Let's start.
Roger. Everything. Roger.
You're ready.
Yeah. Good. Q&A.
Q&A.
That was a short. That was a short session.
Let's start at the beginning, huh?
Okay.
So the agenda of today is RO, right? That's the main topic. Obviously, we're going to talk very quickly about again the problem of biofilm in sand filters, why AFM is such a great replacement for sand, and then we'll dive into the RO topics that you see here on the list.
And we also will discuss at the end, you know, some real cases, three real cases, and then we come to Q&A.
Exactly. Yeah. Housekeeping. You have the possibility to ask your questions through the Q&A function. As we go through the presentation, please write your questions. We'll answer them at the end of the session.
And be careful, there's a red button.
Yeah. This is being recorded.
Yes, this is being recorded. And you can review this on our YouTube channel. Now, we used to have one YouTube channel. Now we have three because we had in pools so many videos. So we made one for Dryden Aqua Pools, one Dryden Aqua Water Treatment. And please subscribe to this, and you will be always informed if we post a new video. And then for the aquarium aquaculture, we have another one. And that brings us to the next slide, Philip.
Yes, so for those of you who have not been able to attend the first session, here's just a quick summary. Who is Dryden Aqua? What are we doing? We are active in three business areas. The company actually started in the aquarium and aquaculture.
With Dr. Howard Dryden, you know, our brain, you know, our brain, genius, marine biologist, the very best chemist I've ever met. Yeah. And he started in aquarium and aquaculture. Yeah. Actually, it was called Dryden Aquaculture. Now it's Dryden Aqua.
That's exactly right. And today, this is about, you know, maybe 10% of our business. The majority of our business continues to be the swimming pool section, which is about 50% of our business.
Where we really have equipped more than 500,000 of pools, and you see what water quality we do with these two good-looking kids.
Yeah, and
the father of them.
Yeah. And a few years ago, we started to expand into the water treatment segment, which today is already 40% of our business. And growing very quickly.
Yeah, and one word to this, you know, when we came to this, you guys in the water treatment, you are even more conservative than the pool guys. You know, I remember, you know, the first Aquatech we started in 2003. Nobody wanted to talk with us. For example, Sychem, he visited us in 2013 and said, this looks very interesting. I come back in 2 years and look if you're still alive.
Yes.
And then two years later, he ordered two pallets. In the meantime, he ordered a couple of
containers.
Yes.
So, but this is where we want to grow, and this is why we have this guy hired. We want to become this dominant factor. You know, we want to do the water treatment should go to 80%, and not by going down the other two sectors. Yes, so this is why you are here, and I'm very happy we have 160 participants. Great.
Yep.
How are we structured?
Where are we? We have two AFM production facilities, one in Scotland, one in Switzerland that we opened up last year. We have a sales and distribution office in Germany, mostly for our Eastern European and Russia market. Then we have 2 sales offices. One is in the US, where we also have a logistics space with 5 warehouses around the US, and one in China, in Shanghai, where we also have a warehouse to supply mostly the Chinese market. No?
Good.
Okay.
So this is an old video explaining who we are and about us, and we give you 2 minutes for our genius man, our brain, Dr. Howard Dryden will lead you through Dryden & Co. Enjoy.
Dryden Aqua is one of the largest manufacturers of water filtration media in Europe. Our activated filter media, AFM, is verified to be the best. We are marine biologists and provide sparkling blue, safe water for over 200,000 swimming pools and clean drinking water for millions of people in Europe, in Africa and Asia. AFM doubles the performance in sand filters and negates the need to invest in new infrastructure. It future-proofs water treatment. Dryden Aqua can process 50% of all the glass bottles in Scotland. The glass is fed into a hopper, all the metal is extracted, and the glass is washed to remove the impurities at 1200 degrees centigrade. The clean glass colour sorted to remove the clear glass and ceramic. The glass is spun in a cyclone and the particles are sieved to make the different size grades. The glass media is activated by a 2-stage chemical process followed by a thermal curing process. AFM is packed into carbon neutral plastic bags and exported around the world.
So we are back.
Yep.
This is actually our old factory. We just upgraded it with €6 million investment to the latest technology, also to be able to do their AFM NG. So both companies, both production are state of the art. By the way, behind me, this is the production. So yep. After this window, they are producing AFM.
That's right. Okay, so next, let's talk about biofilm, huh?
Yeah, I think that's important to understand. And maybe I take a little bit this part, you know, how do bacteria survive in water, actually on surface in water? You know, in bacteria, mainly you have 2 species. You have heterotroph bacteria. Heterotroph bacteria are feeding from organics and produce inorganics. Autotroph bacteria are the opposite. They are feeding from inorganics and produce organics. Let's start with the heterotroph. Heterotroph bacteria under good conditions, warm water, let's say at 30 degrees, if there is enough food, they double every 30 minutes. So very, very quickly. But in water, you know, they, especially if they are oxidants, for example, chlorine, you know, it's difficult for them to survive. So they want to survive, and how do they do it? They look for any surface that is in contact with the water. Within few seconds, they will reach a surface and they attach to this surface. And immediately they excrete mucus. No, not mucus. Mucus. I have a problem to say this. Well, it's a slime, you know, where they cover themselves. And then they grow, they double, and this goes exponential. And then this biofilm becomes thicker and more stable against oxidation. So this bacteria mass covered with this slimy mass, is what we call a biofilm. Mm-hmm. And this becomes, as I said, more and more stable against chlorination. You know, also, if you make a high chlorination, like here, 50 ppm, really, that's a high shock chlorination, you will not be able to remove all the biofilm. It's not possible, because chlorine cannot penetrate the biofilm. It has to oxidize from outside to inside, and by this, it's losing concentration, and some of these bugs are stronger very good, you know, in developing biofilm. They hide itself. So you can remove maybe 99.99%, but you always have few survivors. And if they have then all the food, all the good conditions available, then you create through this process of natural selection, you create really strong bugs, the super bugs.
Yeah.
So this is what we see quite often in aquaculture, in pools, and also in water treatment, that through chlorine, very often in chlorinated system, especially if it's a constant dose, you create through the process of natural selection, you get even a higher biofilm problem.
Yeah, that's right. Yeah. So you said all surfaces that are in contact with water will grow biofilm, right? So where do we have the largest surface in contact with water?
I give this to you.
And this is actually, you know, the sand filter itself. A meter cube of sand has approximately a surface of 3,000 square meters. So this is, you know, depending on the size of the system, this could be 95% of the surface that is in contact with water is actually the sand itself. And
now you have two options. You operate it with sand, and you always fight against this biofilm with shock chlorination and air purging, etc.
Yeah.
Or you do go the smart way, and you go for a bioresistant filter media.
That's right.
I mean, just to mention, there's another big area, the membranes, which we talk about.
Yes. Yeah. So here we're just talking about the pre-filtration for now, right?
But that has the same will happen on the membrane, so, but that will be your part.
That's right. That's right.
Exactly.
Everybody fights here to get more attention.
Yeah, that's okay. So now we know. Now we know how biofilm is formed. What is the problem, right? The problem in a sand filter with biofilm is that over time, this takes, as Dominic explained, this takes time. This could take 6 months, 9 months, depending on the system.
And let me add this, you know, because the heterotroph bacteria, they double very quickly. But I said autotrophs, they have a doubling time of about 10 to 12 days. And it takes 3 to 6 to 12 months, depending on the load, depending on the temperature, also depending how good you backwash the system, that they move in. But when they move in, they produce the food for the heterotrophs. So this is when this system becomes a lot more dynamic.
Yeah.
And where often in sand filters, you generate more biomass in the filter. So that means you have more biomass after the filter than before the filter. So more downstream than upstream. And this is not really what you want.
That's not what you want, right? Yeah. So what's happening is, you know, after a while, the biofilm leads to coagulation of the sand grains. They stick together, they form lumps. These could be, they become bigger and bigger. And ultimately, your sand filter starts to channel. This means bacteria can get through the filter bed unfiltered, like Dominic explained.
Like highways.
Like highways, they can open up, they can close again. It can be very dynamic, but it leads to a very inconsistent and unreliable filtration.
Because in filtration, the lower you filter, the better. But here you build your highways. It's like if you would bypass it. On top, you know, this biofilm, it will offload from time to time. This comes in chunks, especially if you're channeled, and this is where really you have a high increase in turbidity, and this is really biomass, which will end up then ideally on your cartridge filter in a second, not ideally on your membranes, and that's not what you want. So we have an increase in turbidity, we have an increase in biomass, we have, of course, if it's channeled, it's not filtered. It's like if you would bypass your filter, you have a high increase in suspended solids, and it's just your filtration is not anymore reliable. And if you have a bioresistant filter media, that will not be the case. You know, then you have the same good performance of filtration for many, many years if you backwash it in a proper way.
So the solution is to use a filter media that is bioresistant.
And the best that you can have is our AFM.
So how does the bioresistance of AFM work? What happens is a catalytic surface reaction on the surface of the grain, where smallest amounts of dissolved oxygen will react with metal oxides that are in and on the surface of the AFM grain to form free radicals. These free radicals have a very high oxidation potential, and they will oxidize bacteria that are trying to attach onto the glass. So if bacteria cannot attach, you don't have the formation of biofilm as the result. Now, this is the result of two things, right? One is we're using green and brown glass because they contain iron and chromium oxides for this catalytic reaction to take place. And secondly, we're exposing AFM to the activation. The activation is responsible for increasing the surface area. And so the more surface we have, the more of these free radicals will be formed on the surface of the glass.
Huh? Yeah. So we are changing there really the structure to make it really bioresistant and also to make it filter better. But here really this part, you know, I'm a little bit biologist here. I mean, everything. I'm not biologist, I'm an economist, but I learned a few things from Howard. You know, they want to get to the grain to attach to survive, but that's not possible. And this is why we have this bioresistance. And that's the key, ladies and gentlemen.
Yep. Okay. Jochen, you want to take this?
Yeah, I'm taking that. Yeah. Thank you. So how does it look like with fresh sand? So fresh sand picture on the top left, fresh new media. After 3 days, you already have bacteria grow colonization on the surface of the new sand. That's quite normal. So that's how it looks like. Looks not really nice, but that's the normal way how bacteria grow on surfaces, as we just learned.
It's probably also how it will look on the membranes, right?
Mm-hmm. That looks probably, if we come to that, yes, it looks very similar. What is the difference then to AFM? Yes, look here on AFM now. Here we can see a fresh surface area of AFM, a fresh of sand. But here we have, after 5 years, a very nice surface area like at the start. So why this? Because just as Philip explained, we have this self-sterilizing surface area. There is no biological growth.
Yeah, and you even could test this. You know, this is what you see here on the right side, you know, with the bacterial count 18 and for AFM and 3.6 million with sand. You know, if you have one system with two identical filters, one filter with sand, one with AFM, and you operate it for 6 months, 12 months, you know, until really you have this biological growth. And then you take, after a decent backwash, 5 grams of filter media, you put it in sterilized water, you shake it and put it then on the Petri dish for, I don't know, 72 hours. This is what you will get out. So the takeaway is, with AFM, we have no biofouling, no clumping, no channeling. We just have a very reliable filtration that we will see in the next one. Here again, we have, this is a system they did. This is a sand filter, and this is a AFM filter. I go back to the sand filter. So identical on the same system. What we have here below is the time, you know, I guess this is hours. And here you have the buildup of the differential pressure. So that's the load rate, if you want. So you filter, this is why your differential pressure goes up. At a certain point here at 180 millibars, they made a backwash, and then it was loaded again, they made a backwash. Now comes the interesting part. Here, nothing happens. There is no increase in pressure. That means there is no filtration. This, like you bypass the filter. When it's channeled, it's like when you bypass the
These are the highways we have seen before.
These are the highways, you know, and it should not like this. And you see here we had 11 cycles. Here, this is with AFM, and you see it's very regular. You filter, you have a buildup of your differential pressure, your backwash, buildup of your differential backwash. It's very stable. We also have more backwashes, but shorter ones. You know, why do we have more? Because we filter a lot more. This is why you have probably you have to backwash your filter more often, because you just filter more. But the key one, it's reliable. And that's very important, you know, in drinking water, because for examples of crypto, this is important in pre-treatment.
Yes.
Yeah. If you have channeling, everything will end up on your cartridge filter or on your membranes, and this is not good. This is not what we want.
Yep. Okay.
Talk about performance.
So you can believe these two gentlemen, especially Jochen, who looks very trustworthy, or of course, you know, you can believe independent and verified tests.
Yeah, because that was the experience in Aquatech. You know, they told, okay, I believe, but these are your results. So can I have an independent test? So We went to the most known lab in Europe, which is in France, IFTS. It stands for, I'm very proud to say this, I trained it this morning, Institut de Filtration et Techniques Séparatives.
Very good.
Yeah.
Yep.
Maybe you take over back in English.
So what does this report show us? You see here, you know, down here, you see, this is the picture for sand, by the way. This is a very high quality, fresh sand that was being tested.
0.5 to 1 millimeter.
Yeah.
Listen, butter sand, the best that you get in the UK.
Exactly right. You see a removal efficiency of 73% of 5 micron particles. If we then look at a threshold of 95% removal rate, then you see that we are at 20 microns with sand.
Yeah, this is our threshold. We always put this line, you know, it's media filtration is always nominal filtration. It's not absolute filtration.
Yeah, sure.
And some measure it at 80. 80, I think, is completely nonsense. Others on 90. We wanted to be on the very safe side. This is why we put the threshold line. Do you call it threshold? Threshold on 95.
Yeah. Or limit or whatever.
Okay. So what it is, we filtered down with sand, the very best sand before biofouling to 20 micron.
That's right. So the same test with AFM NG. You see a 94.6, so we round it to 95% removal rate of 1 micron particles. This is always the same as with sand at 20 meters per hour filtration velocity.
1 meter of filter bed.
Which I'm sure you can agree for most applications, this is already a high filtration velocity.
Yeah.
So the lower your velocity, the better your filtration will get.
Yeah, exactly. And we have taken 20. You know, water treatment usually is around 10. Swimming pools is around 30. So we took the 20 to be in the middle. You know, each of these tests cost more than 5,000 euros. So, and we tested different medias, sand, AFM, a lot of glass, all these glass, you can forget that shit. It's really the second best was sand.
Yep.
So let's have an overview on the result.
And these tests, by the way, are all available on our website here with the IFTS test report.
Yes.
Okay, should I take this?
Yep.
Yeah.
Okay, so what do we see here? This is again the comparison between AFM NG grade 1 and sand. What we see here, the light green line here, this is the 95% removal rate of 1 micron particles for AFM NG. And in comparison, a fresh, high quality sand that has a 95% removal rate of 20 micron particles. Now, 1 micron, 20 microns, is that a lot?
That's more than a world, maybe like a galaxy almost. Yes.
Is it?
It's a world between.
Let's stay with the planet. In the training, we said the planet. Let's stay with the planet. But also, you know, you have to remember this sand will biofoul, it will come down this line, and then the difference is a lot bigger. So the reality will look even. Then we get to the galaxy.
Yeah.
Exactly. Here we are on the world.
Okay. Good.
But I think it's impressive.
So now you open your part.
Okay.
Everybody fights here.
Thank you. So let's start before we go into the different fouling properties, or let's say fouling potentials, we look into the membrane module. Here we have a membrane module. Most of you are familiar with this one here. That's the membrane mesh spacer. That's the providing the gap between the membranes. You can see in light brownish here, that's the membrane. You have about 25 leaves in a membrane module, and you have the same amount of sheets here. That means this is the biggest area susceptible to fouling, and where we're talking about in the next couple of minutes. On the other side, we are looking now on the bigger picture. Where are our media installed, and where does filtration has its benefits to help the RO modules to operate in their best performance.
And we start conventionally with sand.
Actually, yes. Look first on sand. How does it look with sand? So with sand, the key components in this desalination process is the media filtration. You have the cartridge filters, then high pressure pump and RO module. So we don't talk about so much about this part here. Of course, this is the biggest affected part of coming from the pretreatment here. So you need chlorination, you need to add some coagulant to it to have a very kind of good operation with your sand filter. That's the standard operation. Of course, you need a sodium bisulfite because you need to neutralize the chlorine, because the membrane will be oxidized over a very fast period of time if you cannot remove the chlorine. So we'll come quickly to this one. how can we improve it now?
And you need air scour, huh?
Of course, sorry, I forgot about that.
Yeah,
It's air scouring. That's very important. Yeah. So you need, in sand filtration, you need air scouring.
Yeah.
So they do chlorination to disinfect, try to disinfect. Honestly, try to disinfect the media. And this is why they have to dose the sodium bisulfite to neutralize it. They need an air blower to air purge, to air scour the sand to remove as good as possible the biofilm. And you will see this in pre-treatments. You will see this in pools. You know, especially if you do a permanent permanent chlorination. So this process of natural selection, you know, where we remove always 99.99%, but you always have few survivors. That long run, you will grow even bigger, stronger bugs. You will have more biofouling problem. It's better. And you know, let's say you're not interested in AFM. One of the takeaway, if you have this situation, do shock chlorination. That's a lot better. You know, bugs are like human beings. They like it to have it always the same conditions, right? So it's much better from a biological point of view to do shock chlorination than to make a permanent.
Maybe we look at now how we can improve this.
Yeah,
with AFM.
If you have AFM bioresistance, do we have to mess around with this?
No, we can maybe just to black and white changes. We come back to this slide, but that's actually the conclusion. As Dominic was just saying, we don't need any chlorination because AFM is self-sterilizing, so there is no need to bring chlorine into the system just to sterilize the filter. You may want to have some shock chlorination for the piping, for the walls of the system you may have, but actually it's the best system would run by not having any chlorination. So you also don't need any sodium metabisulfite to neutralize the chlorine. Maybe also important to mention is that coagulation is also not really needed. In some cases, like organic fouling, you may need to add some coagulant to it. But typically, because we have a removal of down to 1 micron particles removal, we don't need any coagulant dosing to be efficient. Also, as a consequence, the cartridge filter replacement will be dramatically reduced. We don't have any cartridge filter fouling because we remove all the fine particles. Yes, and that's very important.
That's
because
a big cost saving too.
It's a cost saving, cost saving. Also, this should not act as a filter, basically. It's actually a policing. Yes. It's like a policing. It shouldn't really be here to overcome the problem of the sand filter. Yes. So we don't have this problem.
Okay, let me quickly summarize this. He is always so fast, huh? So with AFM bioresistance, you don't need chlorine, you don't need sodium bisulfate. That's number one. Number two, you don't need this air purging. This is a cost in CapEx. It's also a cost in OpEx. And you don't need coagulant. I mean, you will also improve the result if you do use a coagulant, but probably you can reduce it a lot if you still need it. And we are coming to this. And then the last point is the period of changing your cartridge will go down dramatically, usually by a factor of 2, if not by a factor of 4. And if you go one before, you know, it might be that you're in a very warm climate where you say, Dominic, this is not safe for me. I believe, you know, in AFM, but still I have the piping and some tanks where I want to do a shock chlorination. Okay, then do it. And we have seen this also in Bangladesh, remember, where it was quite warm, where we have, where we also make not a chlorination. We go there with chlorine dioxide because it's a lot more efficient in removing biofilm once per week or every 2 weeks to remove it. In most cases, it's not necessary. It's not necessary because of AFM. So that's up to you how deep you want to go. But from the media itself, you can do it without any oxidant.
So let's say, as a summary, is we can immediately replace sand in any existing system, and you just can keep your operation as you're doing it today. We would recommend anyway to run the system like we see here on that slide. We can really optimize the system as best as possible. Right?
Sorry to tell you, but you're wrong. Nearly every. Because if you don't have a backwash velocity, you like this joke. It's an internal one.
It's an internal one.
Sorry. If you're down on 15 meters backwash velocity, we can't do anything.
Let's continue.
Good.
Fouling.
Fouling, huh?
So we took a look on fouling. Different fouling problems exist on that membrane market. So biofouling is one of the key. We talk about that constantly now. So biofouling is the biggest critical problem in membrane systems. You can see here a membrane which is biofouling. You can see really that's an additional layer of a surface which really provides for some very bad operation of your membrane system.
Looks a little bit like the sand that we showed before, right?
Yeah, exactly. Yes, and then maybe the worst thing is if you can see something like this here, then you really get into big troubles with your membrane.
That's the mesh.
That's the mesh spacer. Yes, really. That if this is blocking, then you have a problem. With AFM, we can really make sure that this will not really not happen here, because this mainly happens because media filtration generates too much fouling, and then you have this kind of problem. So particulate fouling, that's the next step. So you can remove with AFM down to more than 5 micron, like sand cannot achieve at any time. Yes, suspended matters are here removed with media filtration, of course, but much better with AFM. The next step then would be colloidal fouling. Means the next down in particle size. We go here to talk about 5 microns. So we remove 5 microns more than 95%, maybe even 98%.
Oh, no, with AFM-NG, we remove 99.9%. At
Of
20
5
meters
microns.
of 5 microns.
Yeah.
If we
Exactly.
go lower, then we go there. So I think, yeah, particle is just, we could take particle and colloidal together. Particles are the ones bigger than 5 micron, colloidal are the ones smaller than 5 micron, and we can remove a big part. And I think especially the colloidal fouling is important for us because, I mean, the particles still would be kept in the cartridge, 5 micron cartridge filters.
Which shouldn't be like filtering, it's just your
Policing.
police filter.
Yeah.
Yes. Then the next one down is, of course, like organic fouling, which is precipitated organic matters. They can be dissolved and precipitated. Typical humic acids, you need polyvinium chloride to overcome the problem with humic acids, which are dissolved. But if you add some coagulant to it, we can remove it perfectly with filtration, even much better with AFM.
Or free silica, right?
Or free silica,
With PAC, you make aluminum silicate, this you easily can remove.
Exactly.
Otherwise, we can't do it. Yeah.
And that's important. It's like the removal efficiency of AFM can really remove then these fine clay and especially silt particles. Scaling, that's not really a topic of filtration, but just to complete the list of fouling of the membranes. This is when the salts in the water exceed the solubility limits, then they will precipitate on the membrane, and this creates another problem.
Yep.
And there you need your anti-scalants, huh? Good.
Then you need anti-scalants.
Okay, so if we summarize, no, not yet, huh? I'm on too early.
Yeah,
You're
you're too
fast.
early. Too
See,
fast.
I'm on speed,
That's not
right?
good.
I'm on
That's
speed,
not
so,
good.
okay.
No, we have
Everybody
all
likes
that.
to have
Good.
some control here. Let's look here on what are these fouling
This is actually an
creating.
important one.
Yeah, that's actually key.
Yeah.
A little bit more into details now. Here we have the membranes, as you have seen before, the membrane module. They are in a like a sandwich position. You have here in the middle is the spacer. The water flows from left to the right. The water is forced through the pressure through the membrane. So you generate permeate, and that's permeate on both sides, of course. And because you have a flow rate and you remove water, then you generate a higher concentration of salts on the membrane surface. That's increasing across the membrane because you remove always some part of the water through the membrane. So what does it mean here, technically speaking? We have a laminar flow rate on the outer surface, on the surface areas close to the membrane on both sides, of course. That means we have here no shear forces. That means everything which comes in as a particulate fouling or even as salt, they will start to concentrate on that level here, on that membrane surface. So we talk about fouling here. That means everything which comes in will then attach to the membrane surface. It can be any fouling from biofouling, which is the worst one, actually most difficult one, but can also be particulate fouling. They will attach to the surface and generates actually almost like a second layer of membrane. It's not a membrane, but it generates like a resistance of the water to flow through.
Like a second and a third layer.
Like a second and third layer. It's a combination of biofouling, then particulate fouling. And most problematic is that you have an increase of salt concentration in this area between the membrane and the main bulk flow.
And what is then, okay.
That's the concentration polarization. So we call this concentration polarization layer. This is naturally existing because salt is rejected by the membrane. There's only a specific amount of salt passing through the membrane. That's not 100%. Maybe 99.5, 99.8% is rejected by the membrane, but some salts are passing through the membrane. Nevertheless, the water here in the flow rate is up concentrating, so you have more higher concentration of salts here. The worst problem you have is that you will have more concentrated salts here if you generate these fouling layers. So what does it mean? You have a higher osmotic pressure. That means you have more salts on that area as you would have if there would be no fouling layer. And because there's a laminar flow, these are not removed by turbulent flow rates.
Yeah.
So if my osmotic pressure goes up, what does that mean?
Yeah, osmotic pressure, that's actually the key. We talk about reverse osmosis. So that's where osmosis, the word osmotic comes in. We actually do the reverse of it. That means we need to overcome the natural osmotic pressure. What we do in this process, we generate a higher concentration of salts. That means a higher concentration of osmotic natural pressure. So we need more pressure, more force, more energy to push the salts through the membranes.
And is this significant? Let's say we are in seawater desalination.
Yes, seawater diesel, that's the biggest significant issue you can have. You run these plants at around 60 to 70 bars. Let's say take 70 bars.
And then when your osmotic pressure goes up, then you have to increase this by 0.1.
No, actually 2 bars, 3 bars. This can be really dramatically go up because the salt concentration is up concentrating here, and then you have that's a really energy intense problem. Yes.
So my understanding it's anyway, the osmotic pressure by time anyway will go up because of the salt concentration, but that will be highly increased by this fouling, particle and biofouling.
Yeah.
And this is where you have to put in then from 70 bars to maybe 72, 73 bars. Yeah. And at that volume, that will be a big increase in energy consumption. And
but not all the plants they run at, they can increase the pressure. What the consequence is that you will actually lose more and more of your productivity of your water. So that means you will have less water going through. If you have this situation, you can see here on the downstream of that element or of a system.
Okay.
So let's go in to look in what are the consequences of this concentration polarization. Here's some nice picture. We will explain you here through the explained concentration polarization issue. Increased operating pressure, we just talked about it. Increased operating pressure because of highly increased osmotic pressure through to more salt in the water.
So we have visited some of these RO plants. There were huge motors.
Yes.
So if you have to increase this
then
is
you pay some more electricity cost. Your bill will dramatically increase. Yes. Especially if you have biofouling, as you can see here on a cut-out membrane, you can really see you get really a lot of material away. This is probably like a combination of biofouling with particles. Yes.
Yeah.
So this is really kind of the dead of the membrane. Another problem is scaling. You can see here there's a little membrane left, and that's really like calcium carbonate, mainly, usually calcium carbonate with many other precipitates, which then leads to the problem of a poor permeate quality, higher salinity. Why is this?
Oh, that's what you said before. The membrane always passes the same amount of salt.
Perfect.
But if your water flow of permeate goes down, you have a higher salinity.
Exactly. So the membrane always allows the same concentration of salt pass. It's a dilution question.
You see what we learned in 1 year, Jochen, is unbelievable.
Yes, it's great.
And we are not the guys who are learning fast, right?
Okay, the consequence is you need a high frequency IPs. Problematic is if you're already at that stage, you can see on the bottom 2 membranes, when the biofouling leads to a mechanical hydraulic damage, then you have damaged membranes you will not be going to clean because you need to replace them. So that's 2 different fouling problems. One is typical biofouling here on the right side, iron polymer. That's when you have iron in the water, you dose some coagulant and flocculant, you generate really a problem that it can issue here some of these problems. Actually, AFM will avoid this problem.
Yeah, and especially because it's not channeling. Because, even if it's channeling, coagulation is not working anymore. It's passing and it will end up ideally in your cartridge filter, not ideally in your membranes. So AFM really will solve all these problems, big savings in energy because osmotic pressure will not go up so quickly, better permeate quality. Honestly, I think we will make today not too many friends in the cleaning guys, right?
No,
disinfection guys, but that's what it is. Sorry, guys. Maybe also not for the membrane guys.
Yeah, exactly.
Well,
so we help to extend the membrane.
Cartridge guys, they won't like us, maybe, right?
Yeah, but also the membranes, if
less replacement.
Less
Yeah.
replacement.
But guys, maybe we make the solution a little bit better, and maybe that's pushing up. What's the last point?
Okay, loss of our membrane warranty is that if you reach this point, you probably lost in the meantime your membrane warranty. That means all your nice membrane replacement you have agreed with your supplier is lost. So again, higher energy, loss of money because you need to pay much more for your membrane elements by yourself.
Now it gets
so
expensive.
It gets really expensive. And actually more important, downtime. Big diesel plants, if they don't operate, they cost more money for the downtime.
So we split now the RO world in two groups, right? The operators who will love us because their costs will go dramatically down, and some of the suppliers who will not love us.
Okay, Philip, I think you want to
also
maybe
the EPCs and OEMs will love us, right? So okay, so let's summarize AFM compared to SAND when it comes to fouling, and then we move to UF, right? Next. So we are talking about the different fouling types. So biological fouling, AFM, as you know now, is completely resistant to biological growth. So we have no biological fouling in the media, which you don't have with sand, obviously.
Yeah, and remember what I said, we use in aquaculture fluidized sand baths, really sand filters are also biofilters, so they also generate biomass, and this is, that's not so good.
Then when it comes to particulate and colloidal fouling, also, significant differences with AFM at 1 micron and best sand at 20, and only if it's fresh.
And the moment where it's not fresh, when it's channeled, I mean, this difference becomes a lot bigger. And this is also where you get in the next point in problem. If you work together with coagulation, you have a channeled filter bed, it will pass your filter. There's no chance to hold it back. And here you have with AFM a much more reliable, robust situation.
Okay.
Scaling.
No scaling,
effect.
no effect, right?
That's not our job.
That's not our job. Yes. Not present.
So for this, we have all your guys out there, anti-scalants. How are friends called out there?
Let's hear from H2O Innovation. Hopefully, some of your friends are here. Genesis, H2O Innovation.
Yeah, exactly. Genesis.
Welcome.
I met them in South Africa.
Exactly.
Nice guys. We had couple of beers together. Was good.
So then look on the other options. So we not only have sand as a, call it, competitor on the market, we also have ultrafiltration. Most of you are very familiar with UF because that's the newest development. They didn't know about AF, or you may not know about AFM, but I can show you here why we are actually very competitive near to UF. So sand is filtering, as we just talked many times now, down to 20 microns, and it loses performance after that. If you take AFM, we go down to 1 micron. So now we look on the scale here on the bottom here, process for separation. We actually are within the microfiltration area when we start at 1 micron removal.
Without coagulation flocculation.
No coagulation flocculation. If we then add some coagulants to it, and even maybe flocculation too, that we can really remove particles down to 0.1 micron. We are in the range of ultrafiltration. It doesn't need a lot.
Yeah, and on top, we remove substances which are in solution, phosphates, for example, also, if you have fumic acids, you don't have phosphates in the water, don't have biological growth. So again, I mean, UF is absolute, we are nominal, but nominal down to 95%. So yeah, I think there is a role for both, and for all of you, you say, hey, I trust really only in UF, but I need a pre-treatment. Better to use AFM as your pre-treatment than to sand. Maybe you can make it smaller. You can operate this pre-treatment
that's a good point. That's a good point. Yes,
I always bring good points.
I just want to mention this. You may run the UF membranes at much higher velocity, at a higher specific flux rate, if you use AFM before UF.
Okay,
that saves you on UF.
Okay, my idea was to run the pre-treatment at a higher, but that's even better. So we can sell more AFM. Better, Good. I mean, okay. So what are the benefits of AFM versus
no
UF?
disinfection cleaning chemicals. So we don't need cleaning chemicals. Why do we not need cleaning chemicals? Chemical enhanced backwash is a typical process you need to do with every membrane. That's required by the UF membrane suppliers.
So that's really to clean this.
Exactly. This
UF
is
membrane.
Mainly biofouling. Again, it's a biofouling issue here. So consequently, our system with IFM is much more robust because we can we are more happy to take bigger peaks of loads, which may not be really good for UF.
Yeah, so peaks is never nice. You know, we also like to have it constant.
Yes.
But if there are peaks, you know, in turbidity, etc., it's because it's normal. It's easier to compensate for this. With the UF, it's more difficult.
It's much more tough. Yes, exactly.
Yeah.
Yes. And of course, lifetime. That's a big figure. I mean, this is a double of the figure. Yes.
Yeah.
And even our investment costs are lower, but that comes after 20 years. With AFM.
If it's properly backwash, 20 years.
Yes, 10 years, typically average membrane lifetime, warranties typically between 5 to 10 years. Again, we mentioned before, you need to improve the filtration process, coagulation and flocculation. That's difficult for UF membranes because they don't like too much different type of charge of coagulants or even flocculants more bad. So you can use coagulants, flocculants without any problems, any cationic, anionic, which helps to improve the floc formation, and we can remove it with AFM.
Right.
Yeah.
Even, as you said, dissolved.
Yeah,
organics.
especially with the Ng because it's non-polar.
Exactly,
filter
non-polar,
media.
hydrophobic, yes.
Yeah.
Important, I think.
Lower capex, yeah. It's cheaper, that means it's cheaper. Is it a lot cheaper, AFM compared to UF? It's 10% cheaper, 20?
I think you need to go more, yes.
50?
No, I would say it's actually 3 to 4 times more expensive going with UF.
300 to 400%.
Yeah, that's a lot, yes. And that's all together. I mean, talk about capex, maybe you should add here OPEX into it, but really it's 3 to 4 times more expensive.
Okay. However, we have nothing against UF. We are happy to do the pre-filtration before the UF. We're happy to do this, but we believe, and we will prove it in the coming 12 months, you know, that even just with a good AFM filtration, well-designed AFM filtration, you will not need it. You will end up in a very similar result. Let's go into some project, and maybe I take the first one because I was also involved in this. This is a project, an existing plant in South Spain. You see here 16 very nice Culplus filters. By the way, they are the very best GRP filters in polyester. Hello, Armando. Hello, Jan. That was a short spot, right? A promotion spot. So very nice installation, as you can see here. And I think it's 15 years old. Yeah, they have some problems, not because of the filters. You see a little bit the size, you know, it's 68,000 cubic meters per day of permeate. It's the pre-treatment is 128,000 cubic meters per day. And if you look at the water quality, it's pretty shit, huh?
It's actually quite shitty. Yes,
yeah, okay.
Yeah. So it's if you look on that, it's SDI of 5.6. That's already tough. Actually, in this plant, it's going more towards 6. Problem is here that the sand means the filtrate after the sand filter only 4.5.
Yeah. So you come in with 5. Before the sand filter, after sand filter 4.5. I mean, yeah, that's not great. And even on the cartridge filter, you know, 4.36, 5 micron cartridge filters, they have to replace these cartridges. They are here in the back, you know, every 3 months. And it's not just a big cost, you know, it's a really lousy job to do. You know, there are 2-3 people, you know, you've seen this. I'm happy I don't have to do it.
Plant downtime. Yes. Yeah. Maybe you have to mention here that we run here really at a very high velocity.
Not we, they.
Let's wait. They run at a very high 21 meter per hour flux rate, which is probably quite crazy high.
That's crazy. Yeah. And also only have a backwash velocity of 22. And honestly, we cannot change this. The only thing we can do are 2 things. We can change the media and a small part of the process.
And you can optimize the process.
Yeah. What is wrong in this? You know, number one, and that's a learning, you know, and that's a learning, even if you don't want to work with AFM, etc., that's a learning you should take. You know, always you use sand filters, and you learned I have to do air purge, you know, to scrub off the biofilm from the sand, and I will do this maybe to 90%. This is why I need air purge. Yes, this is true. But if you have laterals, never do air purge. Ladies and gentlemen on the call, please never ever do air purge if you have laterals, because you will just mix up the filter bed. You will just get all your air here in the middle, you know, 2-3 centimeters after the pipe. You will get all the air. So you will create a big channel. You will mess up the filter bed. You will create even channels. You have dead zones out there. This is completely wrong. If you do air purge, you need a nozzle plate. And maybe you say, this guy is stupid and he's wrong and he doesn't know, he's only a pool guy. You're right, I'm only a pool guy. But I can preview this. These are 2 filters. One again is my friend from Colplus, very good. And this is in a backwash mode. This is not with air, this is just with water. And here you see it's backwash down to the end because they have a perfect lateral configuration. And here you see it's only backwashing in the middle. Now remember, this is with water. Yeah. If you would have air, also these Colplus filters would look exactly like this, even worse. You just mess up the filter bed in the middle. You're not backwashing, you're not cleaning it. And you would need a very high backwash velocity in order to reclassify the bed, in order to get proper fluidization and to reclassify the bed. So if they would stop to do this, fill in fresh sand, then the result would look better. Not a lot better, but by assumption would be instead of 4.5, maybe 4.3 after the sand filter. So that's a takeaway that you can take from here.
So if you air purge, then only do it with a nozzle plate?
Only with a nozzle plate.
Yeah.
And Philip, maybe you go here. You explain us the bed expansion.
So this is
to the video. Yeah.
This is a great video showing how the filter bed expands during backwash. You can see how
this is in IFTS. This is in this France lab where they test AFM at a backwash velocity of 40 meters per hour. And now you see, this bed expansion, especially now it's coming. You see it, and you need this bed expansion to get the particles which are in the filter bed to the top of the filter bed.
Exactly. And you need a bed expansion of a minimum of 15% to properly fluidize the bed. You can see this here now very nicely. We actually recommend 20 to 25% as the ideal.
The higher, the better.
The higher, the better. Also, when it comes to backwash, a fast and short backwash is better than a slow and long backwash.
Now, gentlemen, this is not in all cases of your life the case, but here in backwash, it's really short and fast is the right solution. Yeah. And why is this? Because you want to bring the particles to the top of the filter bed, but you really want to wash them out. So you need these drag forces to bring, especially if you have heavy particles such as heavy metals, to the top of the filter bed.
And to remove it,
Yeah, exactly.
And that was a big surprise for me. For me, you were, and you still are, of course, the heroes, your water treatment people. But in one thing, I was really surprised, and in a way also surprised, about backwash velocities. I mean, in pools, it's clear that we backwash our pools at 50, 60 meters per hour because we have these side glasses. We need at least 15% of bed expansion. But in water treatment, many people I spoke, they said, well, I filter at 5, I backwash at 15. This is not a backwash. Filtration means to collect the particles in a filter, but also to backwash it. It's like a bin. You have to empty it from time to time. And you cannot compensate it just with time.
And 60 meters is actually also part of the German DIN standard.
Yeah, but that's also, to be fair, that refers to 0.7, 1.2 millimeter sand. So if you go to a lower sand, 0.4 to 0.8, it's lower.
Okay, so if we compare the same particle size and shape for AFM and sand, in order to get to the recommended filter bed expansion with AFM, depending on the layering of the AFM and the density of the water, you will need a minimum of 20 to 50 meters per hour backwash velocity to properly lift the bed. Whereas with sand, because sand is approximately 20% heavier than AFM, you will need 20% more backwash velocity to achieve the same expansion.
Same size grain always need 20% more because it's 20% more heavy. And all the sand I know, the finest is 0.4 to 0.8. We also have a grade 0, 0.25 to 0.5 millimeter. Our grade 1, we can go down to 30 meters per hour. If you want to go lower, down to 20, we have to compensate this more with grade 0. So as in this case, then nothing to do with performance, just to compensate that we have this bad expansion, and this you cannot do with sand. So
okay.
So to summarize, sand needs air purge to rub off the biofilm as good as possible. AFM does not need this. If you do air purge, you need a nozzle plate, which is a much higher cost than laterals. Bad expansion, you need 15%. You need a side glass in your filter that you see that what you have. Otherwise, you're lost. And this will need 20% higher backwash velocity with sand than with AFM. With AFM, again, we can go down to 20. If you come with a project, even if it's a really great project, and you say, I only can backwash at 10 meters per hour, we will not supply you AFM. We are not doing this. Back to our project in Spain.
Exactly. Just now back in our project. So as you just learned, we want to have a minimum bed expansion of 15%. So here we have a combination of our grade 1 and grade 2, which is a support layer.
Remember, here we have a backwash velocity of 22 meters per hour. We cannot change it. It's installed. It's a retrofit. So we have to adjust our layering to compensate for
exactly.
This.
That's what I did in this project. So I was looking here on our IFU handling manual. We have here all of the data. You can download it from the website. Here you can see at 22 meters per hour, we just are above the 15% bed expansion. That's why I combined this with the AFM grade 0, which is a finer grade, which is more easily expanded. And here you can see at 22 meters, we expand already at more than 25% of the bed. So this is very important that we really want to have a good bed expansion to really remove all of the collected particles during filtration.
And now for these kind of projects, of course, you can read the IFU, but come please to us, especially to Jochen. He will help you in this, really to get best out of this software. Remember session number 1, the filter is the hardware, the filter media is the software, and to do it in the best. And he even developed together with Matthew, thanks to both of you, a fantastic calculator. It's not yet on the website, it's still the beta version.
Yeah, it's like a beta. We still test it internally. There's still some things to overcome, but it looks quite good that we hopefully launch it within this year.
And then you don't have to call us, you go to this and just place the order.
Yes, but I think better you call me or you call anybody of our team with your questions you have to AFM.
Yeah. Okay, but for example, in this project, how is your layering?
So here we have first the grade 3 layer because we talk about the lateral. You need to cover the lateral with the grade 3, which is important because this is also bio-resistant. We don't want that any bacteria.
Not anymore filtering, it's just support, but it's bio-resistant.
Yes.
Yeah?
Okay, especially because that's below the flow rate. So we don't want to have this bacteria grown below your laterals. So then grade 2, which is a support layer for the grade 1 coming up here, but also grade 2 is a good filtration.
Yeah, already the grade 2 filters down to 5 micron, grade 1 to 1 micron, grade 0 even finer than 1 micron. But really here, we needed to compensate it for the backwash. So here we use the grade 0, not just to improve the filtration, really to compensate for this low backwash velocity.
And important, this is a retrofit, so we really adjust our layering to what we have available, 22 meters per hour velocity. And of course, this is a very high filtration velocity, of course.
If you build a new one, if you contact us, our recommendation would look different. Filtration velocity would be lower, backwash velocity would be higher. But even in this retrofit, we are very optimistic to reach less than 3 SDI and also in turbidity. And I think that's kind of conservative number.
Yeah, I think we just give no lower 3 because that's what they need.
Where is your expectation?
I would expect we are somewhere between 2 to 2.5.
Okay, which would be half of sand.
Yeah.
We will find out this because the first truck goes out in 2 weeks and first filter will be filled, and a week later the second filter will be filled, and then we let it run for 2 months, because we do a little bit different of configuration to fine tune it, and then we will do the rest, and then we will post it, hopefully, the good results on LinkedIn soon.
Yeah, and I can show you we can achieve that because we have another project, which is the next one here, in Spain. So Spain is a nice area, a lot of diesel plants, and also a couple of problems they have there, yes.
Yeah, okay, tell us.
Okay, look here. 18 filters here, look, that's really a big plant. And why do we have, for a similar size plant, so much more filters? It's because we have, we run that at lower velocities.
3 meters.
Yeah,
3 meters. This is very low.
I mean, I'm
gravity flow.
That's a gravity filter flow. Yes, even gravity filter low for gravity filters. Yes, but why do they need to run those so low? I will just explain to you. First of all, we did an analysis in our lab. Matthew, thank you, our CTO. He really helped us here. We found out that the the size of the particles are between 2 to 5 microns, of almost 60%.
Okay.
So that's really a big problem. So sand filters, they have all of these sand filters. You see a lot of sand filters, nice installation, but not really helpful. So what we did here, we supplied our pilot unit. We wanted to show and demonstrate that we can achieve a much better quality. So we agreed to this and we supplied these pilot units. Actually, we make them available to companies who are interested in for testing this for larger size.
Not for free. Not for free. And
Yes.
we want to do this for bigger ones. So if you say my 1 cubic RO plant, I want to pilot with your unit, that would be not.
You can just use this one. You can buy it because this makes more than 1 cubic meter.
Yes, exactly.
Okay.
That's a good one.
Yes. And actually, that's a key point is the size of this pilot unit really allows us to really scale it up to big size plants. Yes, this is important. We don't want to make it too small, and too big doesn't make too much sense as well. What did we achieve here? We have achieved here, not we, actually they achieved an SDI of 2 to 3 with the SDI of 5 to 6. Actually, the SDI is okay, but the problem is they only run it at 3 meters per hour.
Okay, so what did our pilot bring?
Yes, so what is our pilot bringing? So we tested it now almost for 2 months, 2 months testing, and here you can see what we achieved. So actually the filter we shown before, they have a SDI of 2.3 around over the same period of time at the velocity of 3 meters per hour, filtration velocity. We achieve with an 8 meter velocity already an SDI of 1.3. I mean, everybody who is watching here now, he will say, oh, actually, that's what I'm getting with my ultrafiltration membranes.
Yeah.
Yes.
Okay, that's why.
Yeah.
Okay,
that's why.
That's why. Yeah.
Yes. And I didn't just pick the best figure during the period. Yes, which you can see here. That's what we really had here. That's the average. Is the 1.3 of what we achieved over the period. You can see there's actually a lot of time below 1.
Yeah. So what's that peak there at 3?
Yeah, this peak here is because we were running it for a longer period, 1 to 2 weeks without backwash, because we wanted to see when is a breakthrough because of these fine particles. So that's why we had this here. We did the backwash, and then we came back here to that. Again, you can see actually below 1. So yes.
Yeah, but I think 1.3, that's exciting. That's really exciting. You know, that's compared to 2.3. So I hope we get here soon.
Yes.
A next step?
We get the next step. Yeah. So let's say the next step is we add this type of layering to our filters, to these filters. So these are nozzle plate, important to mention nozzle plate. So we don't need grade 3. We start with grade 2 as a support layer, so cover the nozzles of the filter. Then we put, again, a combination of grade 1 and grade 0 here, because we still have not our required backwash velocity to go to have a good bed expansion. So we have only 25 meters.
But again, you don't have to mess around with this. We will do this, or Jochen will do it. And if you're overloaded, I will help you, Matthew, Howard. Yeah.
Exactly. So what did we achieve here? So as you have seen before, that's the result from the normal operation. Here now we talk about the 8.6 meter, which is kind of the peak, the max flow rate defined for these filters. At 25 meters per hour, so we achieve here between 1 and 2. That's what we will achieve, and what we have shown before on the slide. We achieve 1.3, and that's what we already discussed before we even tested. We said we will be below 2.
Yeah. So I think these guys have no excuse not to place a big order, right, until end of the year.
No.
Okay.
Let's go to the third case. That's not anymore in Spain, so we jump a little bit more to the Middle East, Africa. Here, a project on the Red Sea.
Yeah.
32,000 cubic meters. Actually, the plant runs at higher capacity as planned. So here, the filtration capacity should be 100,000 cubic meters per day. The good thing here is they can run at the moment at 6.5 meters. That's what they do. Yeah, and they have a good backwash velocity. So that's almost like a perfect situation for us just to go there and say we can achieve a better quality.
Whoever made this design of this pre-treatment, he made a very good job.
Yeah.
Yes.
Yeah.
But maybe
he's on the coast.
From Spain, yes. Probably also from Spain.
But they have an SDI problem, huh?
Yeah. So they have, again, so SDI and feed for 5 to 6 that you find in many desalination plants. That's something normal. What is not so normal in this case is even if they run at only 6.5 meters, they only achieve a 3 to 5 SDI. So why is this the case? I will quickly show you here as a first slide what they found out. So they found out they have very fine silts around 4 micron particle size.
And that's too fine for sand,
Too fine,
especially when it's coagulated. Yeah.
So they did some analysis together with us. So we did some analysis in our lab again, like we did before. Actually, offering this to our customers, to help you to identify how can we optimize your system, not just by theoretical approach. We also have our lab in Scotland where we can do also practical support.
So we have their particle size analyzer and all these things. How much of water would we need for this?
Maybe 1 liter. Yes,
1 liter. So that's
typically
an easy one.
Collect over a week or two, samples so that we have
or two, three samples.
So that we have a good average of what the plant is doing. Here in this case, we have, again, like in the other plant, we have already between 2 to 5 microns. We already reached 50% or more particles of small sizes. As you have seen before, customer did the same. His analysis, it's very fine silt. And the problem is during the torrent season, runoff water, you can see here the pictures, they get a lot of clay into it. So it's even more smaller particles.
It's coming from the desert, yeah?
Yes, that's coming from the desert. So it washes it, and that's the intake of the system. So what they did is they measured the intake of the system up to 2 kilometers out of the sea, and they found these fine clay and silt layers already even at 2 kilometers. So there's no chance. I mean, you can extend it to 3 kilometers, but that becomes very expensive and probably not feasible. So the only solution.
The other solution is to go for a better software, right?
Go for a better software. So improve your hardware.
No, software.
To improve your system.
Yeah, to improve your system.
Yeah.
Yes. Good. Let's see, what did we here? Again, these are lateral filters. We add the grade 3, we add again grade 2 on top. As a typical layering, you require grade 1. And again, because like the other projects, here we have a lot of fine particles to be removed. We added a grade layer of grade 0. There's a little difference. We need not so much of the grade 0. The reason why we added here is because of these very high load of very fine particles.
Yeah, so that's the reason here for the grade 0. But again, you don't have to mess around. Give us just your data and we will do the best layering.
Maybe different here is we also add anthracite to it because it can be, in this case, suspended solids load exceed 30 ppm.
Yeah, this we do quite often, you know, also if you have algae blooms, etc. We will not supply it, but we will recommend it. And yeah, we try to get the best solution out of you. So give us the data and we give you our proposal, our solution.
Important to say for the algae bloom, just to mention it here, the anthracite removes only the big chunks. The fine particles of the algae are removed by our AFM.
Of course, yeah, anthracite, this just gives you room filtration. It gives you a longer time between backwashes. I mean, really AFM is for fine filtration. And if we get heavy loads, we need something else. So anthracite might be one of them or other solution. But we are running out of time. Let's go to, this is what we need, always below 3. We haven't tested it yet. We will not test it. We agreed with these customers that we give some media to test, but he has to pay the transport, that we run once, and if we achieve these results, then it will be an order, whatever. And we would do here an online pilot with one of the filters.
We confirmed already, we will always be below SDI of 3.
So our dear friends in North Africa, this is your chance. It's still open. Place the order and then we can start to get here this excellent result.
Okay. We're coming to the end. So last thing I would like to mention is we have a fully equipped lab in Scotland in our factory. We can test AFM and other filter media under different conditions. And we can also now test AFM and other filter media side by side under different conditions.
So big, small. It's the best lab that I know. It's better than IFTS. It's more modern, and we need this for R&D. We need this for do these tests for your water test.
Exactly.
So we are very well equipped with this.
Exactly. Okay. Last but not least, money, capex, opex savings. We do have a simple calculator that helps calculate ROIs on these projects. Really what's important is we're considering energy savings, water savings, chemical savings, of course, and then we're looking at capex savings. Usually in all these calculations we've done, we are looking at ROIs that are anywhere between even less than a year to maybe 4 years.
Yeah.
The majority
I haven't seen one where
yeah.
we were more than 5 years. Not one.
Absolutely.
Not one.
So we can help you with that as well. Huh? Okay. Outlook.
We are nearly finished before we come to the Q&A. Outlook in a week, same place, same time. We will talk about AFM in drinking water treatment, beverage industry, and especially heavy metal removal. So iron, manganese, and arsenic removal, which is also might be a subject for your RO guys. So we'll be very happy if you would join us again. And here you see the agenda.